So, we're here in 129S, and we're down to Chapter 7, and then we're going to talk more about SQL injection, of course. All right, so let's start with the Chapter 7 stuff, which is here. All right, and let me take a look. That looks pretty good. I'm not filling the screen well enough. All right, so talking about session management, which is very important. So HTTP is sessionless. Every single request is just resolved independently, and it does not remember who you are for the next request. So we have to have something added on for you to be logged in and remember who you are. Then this is, of course, a prime target for attackers. If I can somehow overcome your session management technique, then I can move myself to someone else's account. Ask for example, to become the administrator. This happened to me at the Wall of Sheep in DEF CON. I used Gmail on the DEF CON wireless network, which is the most dangerous network in the world, and I thought it was fine because it logs in with HTTPS. But at this time, the Gmail login was HTTPS, but after that, it would send you a cookie, and then it would continue over HTTP. So some hackers wrote a tool called Hamster and Ferret to automate this process, and they could break into anybody's Gmail, and they got in my Gmail. And if you got somebody get into your account at DEF CON, they put you on the Wall of Sheep, and all kinds of famous people from big companies get up there to humiliate you for doing something unsafe on the network. It was very instructive. I've been hacked a few times at DEF CON. It's very educational each time.
How did you get around that?
Google fixed it shortly thereafter by going to 100% HTTPS all the time. And then many other companies did the same thing. So as of maybe 5 or 6 years ago, this almost never happens anymore, that anybody sends an authentication token unencrypted. It's a really bad idea, but everybody was doing it until maybe 2015 or so. Let's see. As people say, the trophy that says I got hacked. No, the trophy there is for students who hack me. And there's been a lot of them. A lot of students have hacked my website, hacked my computers and stuff, and you get extra credit and you get on the on the board if you do that. All right, so in Web 1.0, you just have a web page with HTML files and images just sitting there, no logging in, no Twitter or comment or anything, so there wasn't really any state to steal. But then we have the modern Web 2.0 where people can log in and then each person is seeing different content, and you can put up content like email and tweets and such. And so now we have to know who you are to know what you're allowed to see. And we don't want you to keep having to log in for every page, so it has to remember who you are. Now, there are some sessions that are not with login functions either. For example, a shopping basket. You could be filling your shopping basket, and that's data stored that's different for each user, but it's not exactly a login. Anyway, so typically what you do is you use set cookie. When you log in, it gives you a set cookie, and it sets a cookie name, which can be anything. This one is ASP.NET session ID, and then it's just a long random string of characters. This is the right way to do it. This should just be long random characters that mean nothing. They're not encrypted anything. It's just a random number. And on the server, they've got a database that remembers who that random number goes to. That's the game. So now each subsequent request going back to the same domain, your browser will automatically add the cookie, and so it'll mark every request with who you are, and the server can read this and use it to show you whatever you should see. Now there's a lot of vulnerabilities. You can have vulnerable way of generating those tokens, and you have vulnerability in handling those tokens as they move around. Sometimes they generate a token, but the app doesn't really use it. This is very common. A developer uses a language, the language creates a token, but they actually use a different token, so it can be hard to find. So I decided to do this at Amazon. If you go to Amazon and log in and just look at a page, and look at the get that loads your page, there are a ton of cookies there. And so what you do, if you want to find out which cookie is you just put it in the repeater and then start deleting the cookies one by one until it forgets who you are. Then you can find out it turns out only one of these cookies is actually used to tell who you are. The others are just leftovers, or maybe they have something to do with ads or something. And so that's how you can find out which cookie actually matters. So here was the minimal request. All I needed was the one called xmain. And it still knew who I was. Over here, my name is somewhere. Yeah, there, it's AmCCSF's Amazon dashboard. So when I delete everything but xmain, it still knows who I am. So that was the only thing it was using to actually identify me. All right. So there are other ways to do it besides sessions. There are integrated authentication methods like basic, digest, and NTLM methods. These are mostly used inside Windows networks that automatically send data to the server when you go to a Windows server from a Windows machine. They're very rarely used on the web. I do use them myself. Basic authentication is a really old technique, and I use it just because I'm old-fashioned and I didn't care. For example, this one here, where it says password required for this thing, this is basic authentication. And the way it works is you make a request to the server, and it'll say unauthorized. You have to pass up a name and password. Then the browser will collect a name and password, and then it'll send it up. And it's really old, and all it does is it encodes the name and password with base 64. So when used over HTTP, this is a terrible system, very insecure. But when used over HTTPS, it's okay. It's encrypted. And so anyway, that's called basic authentication, and you'll still see it occasionally, but it's not that popular. It's a really old-fashioned, simple technique. All right, so then there's other ways to do it. If you don't issue a session token and keep a database on the server, for example, you might have a bunch of servers. Like I mentioned before, you might have a company with a website, and now they want to deploy a mobile app on a different cloud service or something. So instead of trying to reproduce the database on the other app, they want to add extra services without having to configure all the existing services. So the easy thing to do is store all the data on the client. And then all the data goes to this other service, so it has everything it needs to know about you. And this is how you get these sessionless state mechanisms like ASP.NET view state. If you want to store a lot of data on the client, this can be done. It is dangerous, and this is what the problem with it. This is these serialization vulnerabilities are based on this. So instead of just having a meaningless cookie that identifies you, where I have to have a database on the server with all the other information, like your privileges, your shopping cart full of stuff, whatever else I might need to know to serve whatever I'm serving to you, you put it all in this view state. And so in the code, you can create an array and just put a lot of items in here and load it in a view state. This whole array will go in there. And you can store strings, integers, array list objects, hash tables, any kind of data you can program. It can get really big. You just have this blob of data stored on the user. Now, if you use the old-fashioned form of view state, it was not encrypted and not signed. It was just a blob of data like base 64. So you could just unbase 64 and modify it. That's how people get in trouble. And there was I just saw a vulnerability recently, the Microsoft SharePoint, I think a few years back. SharePoint turned off the authentication for ASP view state. So if your server turns it off, then it will ignore that, and then anybody can just unzip it, change the data, change my name to administrator, and get in. It's ridiculous. So you really should be signing it. You should have this message authentication code. And the machine authentication code has a secret generated on the client, and it uses the client's MAC address to create a key, which it uses to create this MAC. So if you take the cookie and you try to modify anything, you can't because you don't have the key. And if you try to run it on a different machine by replaying it, it won't accept that either. So it's quite secure if you have the message authentication code on there. So here's indicators. You'll have a data item like 100 bytes long or more flying around. You get a new token item in response to every request. It keeps sending you another token with different data. It looks encrypted or structureless, and it won't let you submit the same item with a second request. So, all right. So here's a guy that made a $15,000 bounty by hacking into Facebook. He found that there's a password reset, uses a 6-digit code, like a lot of them do. It sends you an SMS or an email or something with a code, and you have to type in that code. And the guesses are rate limited here, but they weren't on another Facebook place. So there was a place that wasn't up to date, so he was able to use Burp Intruder and brute force that 6-digit code. And for that, he got $15,000. All right. So, password recovery tokens are often sent to an email address. They're often hidden in form fields to prevent cross-site forgery attacks so that you can only take a request from the official web page it should come from. If you try to repeat that request from somewhere else, it won't have the hidden form field. It's random every time. That's an anti-CSRF token. This is why every time you're doing projects in Burp, the first thing I do is take the original request of interest, send it to the repeater, and just send it with no change, because I'm checking for this. If they have an anti-CSRF token, I won't be able to do that. And I'll have to use intercept, which is more inconvenient. All right. And so you got persistent tokens to remember you, and other tokens to do things like see what's in your shopping cart and so on. So all these things require the token to be unpredictable. It needs to be random, no pattern, unpredictable. What a lot of people do is they put meaningful data in the token. This might look random, but it's not random at all. It's just hexadecimal spelling things out. These are ASCII characters, 75, 73, 65 is a capital A. It's 65 in hex is a lowercase e. This is just spelling out this in hex. So this is not good. People can use this, but this means I can just, if I figure out how it works, I can just change this to somebody else and be somebody else. All right, and I'm just coding things with ASCII using 2 hexadecimal characters per character. So you can put in the username, a numeric identifier, email address, date, time stamp. All these things can be in a structured token, and they often are, but it's not a good idea. Then you can encode it with XOR or base64 or just hexadecimal ASCII codes, and all these are commonly done. Well, I've had a lot of students come to me, developers, and say, oh, I made up my login system. I'm just doing one of these things, and is that okay? And I'm like, no, it is not okay. But this is very common that a developer that doesn't know much about security just uses one of these common transformations to make a cookie and doesn't understand that hackers can easily figure this out. All right, so to find this, get a token and just try modifying in different ways. Change 1 byte at a time or 1 bit at a time, see what happened. Burp has a char frobber function just to do this, to automatically change bits. I think it might only be in the pay version. Anyway, you can try logging in to several users at different times and see what the tokens is. I've done this a lot on apps. And then you see if you get the same token every time you log in as the same user instead of a new random number, that suggests that that is in fact encoding your username or something. All right. And look for correlations. If you have repeating letters, then if you're using, say, XOR, it will just make repeated different letters. If you have base64, it'll often have these equals or double equals in it. You know, you learn to spot these common encoding steps. So use the pattern to try to guess the token of another user, and, you know, find some page like I did in Amazon where you can tell who you are, like it has your username on it. Then try changing that token and see if the username changes to somebody else. And Burp can do this automatically, and we'll play with it a little later. So let's take a look at a...
So in base 64,
what about it?
Repeat character is equal?
It's not a repeat. Base equal is a padding character, because base 64 must be in units of 4 characters. 4 base 64 characters encode to 3 ASCII bits, because a base 64 character only has 6 bits, and every byte has 8 bits. So 3 bytes is 24 bits, and that is 4 base 64 characters. So your base 64 string must be a multiple of 4, and if it's not, then you pad it with equals. That's what that is.
So the equal is the same thing as padding?
Yes, the equal is telling you that the last group of 4 was not full. And so it's just a mark to record that. Here's another amazing thing I learned.
At the end there.
Yeah, always at the end. And there's another thing. By the way, you don't really need it. You could just count the characters. That's why it's funny they made such a big deal out of it. But the other thing that's amazing is base 64 is not unique. When you encode things with base 64, there are some bits in the base 64 that might not be used in the decoded thing. And so you can actually make multiple base 64 strings ending in different characters that will decode to the same thing. Because when you're down, if you have, say, 2 bytes, that is 16 bits. So and let me just talk about this. Let me put up a, this is actually kind of amazing, and I learned this doing a CTF. All right, let me open this up. If you make a little chart, let's talk about base 64. This is good fun. Okay, so if I have A, B, C, D, and this is 41, so this is 0, 0, 1, 0, no, 1, 0, 0, 0, 0, 0, 1. There, that's the A. Okay. Let's get rid of that stupid dot. All right. Now let me just, the B is 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, okay. The C is 0, 1, 0, 0, 0, 0, 1, 1, and the D is 0, 1, 0, 0, 0, 1, 0, 0. There. That's what this is. A, B, C. And actually, all I need is A, B, C. I don't need A, B, C, D. So I'm going to get rid of that, because 3 characters of ASCII. This is now 24 bits. Now to make it into base 64, you break it up into 6 bits. So it's 0, 1, 0, 0, 0, 0. That's the first character. I'm going to put it like this. Then the next one is going to be 010100. The next one's going to be 00101001. And the last one's going to be 000011. There. This is going to turn into 4 base 64 characters. Now, if I only had 2 letters, then I would only need this many bits. But when I encode it in base 64, it's going to take 3 characters, and you see the last 2 bits are not used. So I could have 4 different base 64 characters here, and it would still map to the same thing. This is an amazing thing. When you see the padding, base 64 is no longer unique. It's an interesting fact. But that's all it is. It's just grabbing, putting out the bits in a different size group. All right, let's see. I got a question here. Was I logged into Amazon when I started stripping away cookies? Yes. I think I was logged in. I'm not. You might not have to be logged in for it to put an ad. I was logged in. It saw my name. Yeah, I logged into Amazon. Yes. First, I logged in with a name and password. I made a test account, and then I went to a page that showed who I was and just refreshed it in Burp Repeater, and then I just started deleting cookies until it forgot who I was. That's how I did it. That's how you do it. All right.
So in base 64, you only if you have like one encoder 64, base 64, you match into 4 different kinds of encrypted text.
No, it's the other way. I mean, the base 64 will always decode to one unique ASCII. But the opposite is not true. There is more than one way to encode.
Only the last.
Right, only the last one.
Only the last digit, right?
Only the last group, because the only ambiguity will only be there if you don't have 3 characters of ASCII, but you only have 2 or 1.
It will match up maximum to the 4 different.
Yes, and it's even more than 4. If you only have 1 character at the end, then you have 4 bits you're not using. So it'll be 16 possible characters that would all decode to the same value. That's why I had there was a capture the flag where they gave you base 64 and they gave you the plain text and there was a hidden message in the base 64 anyway. And I said, how can that be? But there's bits you aren't using, so you can encode something there. And that was interesting. Anyway, I've never heard of anybody actually using that for a nefarious purpose, but you could. It's a simple form of steganography, hiding a message in a message. Anyway, here's the cahoots. Maybe enough. I guess I'll wait a little longer. People still coming in. All right. All right, so what encoding will turn this into that? That's MD5 hashing, which your book calls encoding. Technically, it's not exactly encoding because you can't come back. But you could store a username that way, and then you could recognize it when it came in. Anyway, that's what MD5 you can spot because it's a bunch of hexadecimal and it's always the same length. It's 128 bits. SHA-1 is 160 bits and so on. So, you can, all right, anyway. All right, what encoding will do that? That's just hex encoding. You can spot the AAAA is turning into 41, 41, 41, 41, and especially if you're taking the exploit development class, we're using that all the time. And so it's just each character just turns into 2 hexadecimal digits. All right. All right, how about that one? That's base 64. Wait. Yeah, it is base 64. And by the way, you can see this is 3 characters, USE, R equals A is 3, and this is 3. So there's 3 groups of 3, so it doesn't need any padding. It'll turn into 3 groups of 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 3 groups of 3 characters turn into 3 groups of 4 characters. And so way to spot base 64 is it uses only upper and lowercase letters and numbers, and a couple of symbols like plus and slash. It sometimes has equals at the end, but only 2/3 at a time. So you can, but it's not hexadecimal because hexadecimal doesn't use characters like Q and X, and hexadecimal does not make a distinction between lower and uppercase. So when you see upper and lowercase letters, especially if there's numbers in there, and I think there's a 1 in there, then it's very likely base 64. All right. All right, how about that one? Okay, you can spot the AAAA has turned into 50-50 or 5555, and so that is each character is being encoded one by one and changed, so that's XOR. We've XORed it with a constant value, so this changes into some other number, but then it repeats. That's single byte XOR, where the key is a single byte, which is, again, a very insecure system. All those are pretty insecure. But you'll see them all over the place. All right, let's go and take a look at some more of this. So, sometimes the token is predictable. This is another mistake you can make. So if you make a sample of tokens, like make several accounts with similar names and see how they look, then they might be possible to predict tokens. Some commercial implications might be vulnerable. And by the way, if you can install a local server using whatever it is, then you can run, fast many trusts on your own server instead of having to use somebody's cloud service. That might make it more vulnerable because you could really get, hundreds or thousands of examples to analyze statistically. So, for example, if you have sequential tokens, Burp can just try sequential tokens. So you've got some number, you just increment the number and then see who you're logged in as, and as you change this number, you end up logged in as different people. So here they had something like a single byte, and they tried every byte, and 01, 02, and 001 and 02 was not logged in, but some of them did log in as different people. So that's what you'll see if you're able to change a number and it turns you to different people. So there might be concealed, it could be an obvious sequence like that, where you can just add 1 to a small number. That's ridiculously easy. You see that. But then they might have done something to make it a little bit harder. Like we'll see, basically weak random number generators. Here's a concealed sequence. This appears to be random base64 encoded stuff. If you decode it, it just turns into unprintable gibberish. So it's not really base64 encoding of something meaningful. This seems to, again, just random, but it's not random. What you do is render it as a number, and then calculate the difference between the numbers. And you see an obvious pattern. A bunch of them have the same distance, same difference, and when they don't have this 97, they have an FF followed by the same number. So this is actually just adding a fixed constant to a number and then keeping only the lower digits. It's wrapping around. This is basically a straight line. Each one of you, so you can just generate these, and you can even write a Python code that will do it. All you have to do is keep adding this constant amount to the number, and then keeping only a certain number of bits on the right, like the right 32 bits or something. So that's a way to make something that looks random, but it isn't really random at all. So there's various ways. Here's another way to do it with Python. You can just generate the valid tokens with that system. You just keep adding this number, and if it's greater than something, then you just subtract this number and wrap it around. There's another one. You have this pattern. These numbers are 8, 9, 40, 41, 42. This is just counting up. This one is also going up. Notice how it's 58, 587, 590, 592, 597. They're each going up. So the ones on the left goes up by 1 every time. The right one goes up by a varying amount, but not a very big amount. Something going from maybe 1 to 4 or 500 here. So they made another sample 10 minutes later. Now the first number has gone up by 6, but the second number has gone up by 600,000, which is 600 milliseconds. So the one on the right is just counting up milliseconds of time. And the one on the left is just incrementing. So you can totally hack in, and here's the hack. What you do, poll the server frequently to get the tokens. Then when the first number increases by more than 1, another user logged in between. And now you know that, so you keep logging in over and over. You keep getting tokens. And when somebody else gets in, you know that their first number is between the two numbers you have, and their second number is between the two numbers you have. Both numbers are just going up. So now you don't have too many to hunt through, just at most a few hundred to find them. That's why, it's another kind of mistake to make. So Jetty was a Java-based web server, and this used a poor random number generator called a linear congruential generator. These were pretty common, and what they do is, remember the simplest one just added a constant and kept only a certain number of bits. This one multiplies by something and then adds something and does some shifting, but anyway, the point is it basically is the same. It's a straight line where it just keeps the insignificant digits of a number, and once you have one value, you can predict all the rest. All right. So PHP had this a token generated from your IP address, the Unix epoch time, microseconds, and a linear congruential generator. And the problem is none of these are really that much randomness. So in principle, people knew that it wasn't really that many total bits of randomness, and you might be able to get in. And it took Sami Kamkar, a famous hacker, actually wrote the attack tool that would break in by exploiting this lack of randomness. And so you say, how good is randomness? And here's the obligatory Dilbert. Before Dilbert went nuts and got himself canceled, he had a lot of good. So you have random number generator, it just gives you 999,999. Is that a good one or a bad one? You don't know. How do you determine whether a random number is good? Well, this is what you do. You assume that it's random. Then you apply a series of tests to see what is the likelihood of observing this if it's random, and only if you observe something very uncommon. This is how you do it. You can prove that something is not random. By doing a test and showing that something has like only 1 chance in a million of happening, then you have reasonable evidence that it's not random. That's how you do it. So Burp has a thing called Burp Sequencer in the Pro version that will try doing this stuff and actually test every bit of something to see how random it is. And they were able to show that this system here had good random bits, but some of these bits are always 0. So, maybe it's supposed to have 32 random bits, but they aren't all random. So it has less entropy, they say. That's what entropy is, the measure of disorder. And for random numbers, you want a lot of entropy. If you don't have enough entropy, then there aren't really that many bits that vary, and you can try them all. And then there's encrypted tokens, where you actually have meaningful data and you encrypt it with a secret key the attacker doesn't know. This might sound good. If they can't steal the secret key, they can't do anything, but that turns out to not be true at all. For example, if you use electronic codebook ciphers, which a lot of people do, where you just encrypt every block of data separately, then if you have this, turns out to be extremely dangerous. This is what an electronic codebook does. If you encrypt this image, it'll turn into that. You still preserve a lot of the image. You have a block here that's all orange, so that just turns into this block. Every block encrypts to the same thing independently. So it preserves patterns. That's one issue. But if you have a token like this with a random number, something about the app name, a user ID, a username, then a time, you have a bunch of things in a string, and you encrypt this. The encrypted form looks like random junk, but they encrypted this with GES, by the way. Any encryption scheme will work. It's encrypted in 8-byte blocks. So each block of 8 bytes is encrypted into junk. Now, what you can do is you can move these blocks around out of order without knowing the key and without decrypting them. And if you do that, you can take this, for example, I could take this first block and put it down here, duplicating it, and now UID equals 992. Instead of what it should be. The UID should be 218, but by just copying one block and putting it down here, I've now made the UID something else. So I'll observe I've logged in as another user without being able to decrypt it. And you can go even further. If you want to target UID equals 1, then you have to get a 1 here. So you create a user. If I can UID 1, I'm going to be the administrator. So what you do is you create a user with a name carefully chosen of different lengths until you make a name ending in 1, and you try different lengths until the 1 wraps down here. You can generate a block of text starting with a 1 semicolon, and then when you put that in, you're going to be the administrator. It's usually user ID number 1. So, this is, that's why even though I can't decrypt it, I can still exploit it. All right. CBC is the standard cure for this. In cipher block chaining, you have an initialization vector in addition to a key, and you take the output of every block as the initialization vector for the next block. So now, each plain text is not encrypted identically. There's a random thing added, so it comes out different. So now if you encrypt that apple, it just turns into this random snow. So it looks a whole lot better, and this is what people use almost all the time because it's better than electronic codebook. But it has its own flaw. And so in CBC, that will again turn into this stuff. But the problem with CBC is when you decrypt it, if you change one block of the ciphertext, 1 byte of the ciphertext, that will, in the decryption, that will ruin this entire block, will turn into random stuff, but it's used as the initialization vector here, so it's simply XORed here without changing it. So when I change 1 byte here, I only change 1 byte here. That property, I can exploit that property now. So what that means is, if I'm willing to accept destroying one whole block, turning it random, I can change just 1 byte of the plain text without knowing the key. I can't control it, but I can change 1 byte at a time, and of course that can be enough. So here, as I just changed 1 byte at a time of the input, they'll always have this block of data turned into unprintable junk, but then I will change 1 character in the next block. So I change a character here, it ruins this whole block, and it changes that to 8. Then I change the next character, changes this to 2. It's changing 1 character in the cookie, so eventually I'll hit the UID, and now I've made it a different number. As long as I can accept the collateral damage of destroying a block, and often you can, often there are parameters that don't really matter, then I can have a small controllable change in these other numbers. And so if you do that in Burp, there's a ways to do that. Burp has the ability, at least in the Pro version, to do this. And then you'll just get a list of users. So see something like this. Some flips change the user ID to invalid, unknown user, but here's your real user. And then a few of them turn into real users, like Peter Wiener and John Herman. Some of them will happen to hit the important spot, and you get into somebody else's account. So that's the game. And it doesn't take forever, because you're not like brute forcing you're just changing each byte. You can just change bit by bit. So it doesn't take that long to try every possible change. All right. So there's also information leakage. Even if you have a secure encryption routine without any of these flaws, it might reuse the encryption somewhere else. You might find a place where you can put in data and it will encrypt it. For example, it might encrypt your username, which you control. So in that case, you might be able to submit the desired text, change your username to UID equals 1, and get the encrypted form in the cookie, and now try putting that in. So, you know, these are various ways you can go wrong. All right, let's try another Kahoot, which is 7B here. All right. All right, might be enough. Let's see. All right, let's give it a try. All right, so what token type will use the same token every time you log in? If you're encrypting meaningful data, like your username, then it will be the same every time you log in. It won't be some pseudo-random number. All right, which system do you exploit by rearranging blocks of ciphertext? That's electronic codebook. It'll only work if each block is independently encrypted, so the order doesn't matter. All right, which one can you exploit by changing a single byte? That's cipher block chaining. That's the one where changing one byte will do some collateral damage and then change just one byte later. All right, which system uses one block of data to influence the encryption of the next block? That's cipher block chaining. All right, by the way, the solution for all this is you should use Galois counter mode. Then you have an initialization vector that's different for every block, and that is created by a pseudo-random function. So one block does not depend on the next block, and every block is encrypted differently. That would stop all these attacks. That's what's recommended. I got SR, I hope that's the real initials. Pete B, that's a real name. My grader will find that easily. And Cat. All right, good. So, all right, let's see at 6:50. All right, well, let's take a 10-minute break till 7, and then finish this up, and then to demonstrate more SQL injection.